Let's work with draw sheet number 2. From the given pairs of molecules given below, choose which one is a stronger nucleophile. A nucleophile is a compound that is having electrons which are available for donation. So the more the lone pairs of electrons or the more negative a compound is, the stronger nucleophile it is going to be. So the word nucleophile comes in because the compound loves the nucleus. We know the nucleus has got protons which are positive. So if the compound is more negative, it means it's going to be attracted to the nucleus which is more positive, and so it's a stronger nucleophile. And then the compound which is having a more positive nucleus, which loves those electrons from the nucleophile, is called an electrophile because it loves electrons. So starting with ammonia and amine. Ammonia having three nitrogens and then one lone pair of electrons, and then the amine having two hydrogens, then two lone pairs. So we can see that this one has got a lot of electrons available for donation, so it is a stronger nucleophile. Hydroxide and water. The hydroxide has got three lone pairs of electrons. We know the oxygen of water has got only two lone pairs of electrons. So this makes the hydroxide to have a lot of electrons available for donation, and so a stronger nucleophile. If we talk about HS, we can see there's a negative on sulfur, and then the cyanide, there is a negative on the carbon. Now, because sulfur is a bigger atom, and because the polarity of this bond is going to be higher than the polarity of this bond, this is going to be a stronger nucleophile. So the strength of the bond, if you consider the difference in electronegativity for hydrogen and sulfur, hydrogen is in group 6, sulfur is in group, hydrogen is in group 1, sulfur is in group 6. So there is a greater difference in electronegativity, meaning that this one pulls electrons more towards itself. So it has got electrons more towards itself. But if you consider between carbon and nitrogen, these two are very close to each other. So even the pull of electrons towards the carbon in this case is not that high. And so this HS is a stronger nucleophile. What product will be obtained or formed from the SN2 reaction of the following? I've got two bromobutane. Let's put a bromine here at position number 2, and then you have got an hydroxide ion. So for an SN2 reaction, this hydroxide is going to attack from the back direction. If it does that, this is going to be this bond is going to be released, and those two electrons in the bond are going to be taken by the halogen, and so you end up forming something like this with the OH there and then the bromine being released. So from 2 bromobutane to butanol. So that is the product here. Now for the next one, it's the same compound, it's just that stereochemistry has been specified. We're talking about ara2 bromobutane. Now if this is a butane, we know, let's say this is position number 2, we are supposed to have the bromine. We know we are also going to have the hydrogen there, even if we can see it. So let's say I put the hydrogen at the back. Now, we know hydrogen always carries position number 4 because it has got least priority. And then the bromine is going to carry position number 1. The one which will carry position number 2 is this one, number 3 is this one. And for our configuration, we need to write something that is going in this direction as long as the hydrogen is in the back, meaning that our bromine can be here. So this is Ara2 bromobutane, and then the reaction with same hydroxide. This is also going to attack from the back. This bond is going to be broken. So there is reversal of configuration for the product. The hydrogen is still here. But if this was Ara, then the product should be S. This is Ara2 bromobutane. The product is going to be S-butanol, S2-butanol. Then where are we supposed to put the OH? We know this is position number 2, this is position number 3. So say this is the structure that we have, and then I put the OH here. The configuration will still be what? The configuration will still be R. So I'm going to put the OH here. This is in front. So this will be position number 1. We can see now the configuration has changed. It is now S. So that is important to take note. Change of configuration. Arrange the following. I'll queue bromides in order of decreasing reactivity in an SN2 reaction. 1 bromo 2 methylbutane. Maybe first let's write their structures. All these are butanes. We have got a butane, but at position number 1 we have got a bromine. Position number 2 we have got a methyl. The next one also is a butane. Position number 1 we have got a bromine. At position number 3 we have got a methyl. The next one is also a butane. At position number 2 we have got a bromine and also a methyl. The next one is a pentane. 1, 2, 3, 4, 5. At position number 1 we have got a bromine. Now for SN2 reactions, the more substituted a compound is, the slower the reaction is going to proceed. We want to arrange in decreasing reactivity, meaning we start with the most reactive in SN2. So the most reactive is the one which is the least substituted. We can see for the last one here, this one is a primary. Why? Because this carbon bonded to the bromine is only bonded to one group. That's why we're calling it a primary compound. So if I say this is 1, this is 2, this is 3, this is 4, this means that 4 is going to be the most reactive, and then what to be the next? The one which is least. Okay, let me put a dash here and then a dash here. But we know that the one which is going to be least reactive is the 3. Why? Because this one is the most substituted. We can see it has got 3 substitutions. So it is a tertiary compound or tertiary alkyl halide. Now between 1 and 2, which one is going to be more reactive than the other one? So 2 is going to be more reactive than 1. The reason is simple. This group here is far away from the carbon that is bonded to the bromine. So when you are attacking the bromine, the carbon with the bromine from the opposite direction, there's going to be a little resistance from this one than from here, because we have got a methyl which is near to the bromine. So there's going to be more resistance. The more the resistance, the less the reactivity. When methyl bromine is reacted with sodium hydroxide, methanol is produced. Name and write a detailed reaction mechanism for this reaction. Been told when methyl bromine, let's say we have got a carbon here with 3 hydrogens, and then now a bromine. Now, every time you have got a methyl bromine, or let me just say methyl halogen, the reaction always proceed by SN2 reaction. And so what we are going to have here is, on the product, what are we using? We are using sodium hydroxide. Now from the sodium hydroxide, we're going to have the sodium ions and the hydroxide ions. So what is going to happen is that hydroxide is going to attack from the opposite direction. And then we are going to form an intermediate. We are going to have a carbon. This bond is going to be partially broken. And then we are going to have a bond being partially formed with the hydroxide. And then we have got, let me put 2 hydrogens like that. And then 1 hydrogen down here. Now, because this compound has got a lot of bonds, we can see the carbon has got a lot of bonds. Carbon can only sustain 4 bonds. So this thing has got so much energy. We know oxygen is more electronegative than carbon, so is this going to be a partial negative charge? Bromine is more electronegative than carbon, is going to be partial negative. So the carbon is going to have 2 partial positive charges on this compound. And so now the last thing what is going to happen is this bond will be fully broken. So we're going to have the carbon with the hydrogen here, hydrogen there, and then the alcohol there. So this is the nucleophilic substitution reaction, second order. Second order nucleophilic substitution reaction. Give the rate law for this reaction and say the overall order. The rate law for second nucleophilic substitution reaction is given by K, and then you write the alkyl halide. In this case, the alkyl halide is methyl bromine, and then multiply by the concentration of the nucleophile. In this case, is the hydroxide. And then the overall order for this reaction, it is first order in regards to the methyl bromide, first order in regards to the hydroxide. So overall order is second order. You just add those two. What happens to the rate when the concentration of the nucleophile is doubled? So if you double the concentration of the nucleophile, the rate is going to double. You triple the concentration of the nucleophile, the rate is going to triple. And just like that. That is because we are considering this to be constant. And then for the next one, what happens to the rate when the concentration of the nucleophile and substrate are doubled? So if I double the concentration of the substrate, which is simply the methyl bromine, and the concentration of the nucleophile, both are doubled, the rate is going to increase by a factor of 4. Indicate the effect on the SN1 and SN2 reactions of the following. The first one, doubling the concentration. Let me write SN1 here. Let me have SN2 here. What happens when we get to double the concentration of the substrate? Now, the rate of an SN1 reaction is given by K concentration of the substrate, which we call the alkyl halide. And then the rate here is given by K concentration of the substrate and then concentration of the nucleophile. So if I did double the concentration of the substrate for SN1, the rate will also double. But if I double the concentration of the nucleophile, the rate will not change for SN1. If we go to SN2, if I double the concentration of the substrate, the rate is going to double. Or if I double the concentration of the nucleophile, the rate is still going to double. For the next one, what is going to happen? Using a mixture of ethanol and water. Now, if you have got a mixture of ethanol and water, and then you have got acetone just, okay, mixture of ethanol and water or only acetone. So we have got alcohol, ethanol, stroke water. These are together, or you only use acetone. Now, acetone is a polar aprotic solvent. It is polar, but it does not have electrons, which it is able to, doesn't have hydrogens, it is able to use to form hydrogen bonds. So in acetone, there are no hydrogen bonds, but in water, you have got hydrogen bonds. So for an SN1 reaction, what happens is that first the Rx, the bond here just breaks automatically. And then you are going to form R plus and X minus. So when you are using a polar protic, so this one you are saying it is polar aprotic. It is polar but doesn't have protons to form hydrogen bonds. And then here we have got polar protic, meaning that we can form hydrogen bonds. So if I'm using a mixture of ethanol and water for an SN1 reaction, the water is going to be able to solvate. It is going to be able to surround these ions like that and also surround these ions like that. So thereby stabilizing the ions that we have formed. So for an SN1 reaction, the polar protic solvent is good for an SN1 reaction. Now, if you use a polar protic for an SN2 reaction, we don't have a step where this breaks to form ions like this. Okay, we simply have the nucleophile that is supposed to come and attack the alkyl halide and then the bond breaks. So what happens is that when you have got a polar protic solvent, nucleophiles are mostly negative. So the polar protic solvent is going to be able to surround the nucleophile. The water is going to be able to surround the nucleophile via hydrogen bonds. So the nucleophile is going to be weakened such that it will not be able to attack the alkyl halide. And so because of that, the reaction is going to slow down. And so for water, a mixture of water and ethanol is not going to be good for SN2. Instead, the acetone is going to be good for SN2. Why? Acetone will simply be able to surround this one, but it will not be able to form hydrogen bonds. Okay, so that is what gets to happen here. But if you talk about acetone with SN1, acetone will not be good. So basically, this is what we are going to be able to see. So using acetone SN2 is going to be good because it is going to minimize ion pairing and the nucleophile is going to be allowed to attack very well. So you can see this, we have got this nucleophile. You are going to have, let's say we have got maybe anything else that is positive in the reaction. Just the acetone will be able to surround this nucleophile, preventing it from being attached to anything else that can be positive in the reaction, but there are no hydrogen bonds of course being formed, so I mean that it's just being protected from anything else that is positive that is not supposed to attack, and then it is now going to attack the right thing that is supposed to attack. Now let's consider three. Increasing the number of R groups on the carbon. What is going to happen on the carbon that contains the leaving group? The leaving group is simply the halogen. That is what we call the leaving group, and it is found of course on the substrate, which is the alkyl halide. Then what is going to happen in such a case? If you increase the number of R groups, let's say I've got a carbon where I've got your bromine here, and then you have got R, you have got R, you have got R. Then you have got a bromine with your carbon. Let's say you have got R, you have got R, and then you have got hydrogen. And then the last one, you've got a bromine with a carbon, you have got R, and then you have got hydrogen, hydrogen. I can even put another one. You have got a bromine with your carbon here, and then all of them are hydrogens. For an SN1 reaction, the first thing that happens is that a bromine is going to just move out by itself. So this thing will remain positively charged. If you have got a lot of R groups, these have got electrons. Remember, these are carbon containing compounds. They've got a lot of electrons. So those electrons are going to be able to balance this charge which is being formed because electrons are negatively charged. So for a tri-substituted compound, it is going to be very good for SN1 reaction. But this one, which is non-substituted, this is mono-substituted because it just has one R group. And then this is just a methyl compound, a methyl bromine. This one is not going to be any good for SN1. Why? Because if this thing breaks off, and then this will remain positively charged. This positive charge will not be balanced by the hydrogen because they've got less negativity. So because of that, this thing is going to be less stable. And the less stable a compound is, you don't prefer to use it. But for this one, it is good for SN2. Why? Because for an SN2 reaction, what happens is that you are going to attack from the back direction. First, the carbon that contains the bromine, and then the bromine is going to be released. But if you want to attack this direction, you have got a lot of these groups which are shielding this carbon which has to be attacked. And so because of that, you are not going to be able to do it. So simply mono-substituted or those which are less substituted, they are good for SN2 and bad for SN1, and then opposite is true. What happens if you use a stronger nucleophile? If you talk about SN2, a nucleophile, remember, is the one which is first attacking the carbon. So if it is strong, it will be able to attack very much, and then this will be easily removed. Now, for an SN1 reaction, this bond is removed by itself. Okay, it is automatically broken. So you don't need to use a stronger nucleophile because simply what you want to do is just to balance this charge because the bromine has already been removed. So a stronger nucleophile is good for SN2, but it does have no or little effect on SN1. List the following alkyl bromine in order of decreasing reactivity in the indicated reaction. SN1. Now, as we have mentioned, for SN1, those which are more substituted are good. We can see this carbon which contains the bromine has got two groups, so this is secondary. This carbon has only one group, this is primary. This carbon has got three groups, this is tertiary. So for SN1, the tertiary is going to be the best. Okay, tertiary is going to be the best, followed by the secondary, and then followed by the primary. And then for SN2, the primary is supposed to be the best. And primary is 2. Oh, sorry, my laboring here. We've said the best is going to be 1 because it is a tertiary. The second is going to be 3. And then this is 2. Okay. For SN2, it is just opposite. 2 is going to be the best, followed by 3, and then the least is going to be 1 because it is too much substituted, and so it will be difficult to be attacked by the nucleophile. Benzyl chloride readily undergoes SN1 reaction with water to form benzyl alcohol. Write a detailed mechanism for this reaction. Show all resonance structures involved in the stabilizing of the carbocation. So benzyl chloride, we have a benzene ring is simply a cyclohexene. Now I've got alternating bonds. So if I attach the chlorine direct like this is not a benzyl chloride. So this ephenyl group is a group where you attach compounds direct here. But for a benzyl, You don't need to attach direct to the carbon that is on the chain. Instead, you are going to use this carbon, and then to that carbon, that's where you're going to attach something. That's a benzyl. So this is benzyl chloride. Now, because this is SN1, the first thing that happens is that this bond breaks by itself, and then you are going to be able to form alternating bonds, of course. We are going to have this now will remain positively charged because this bond has been broken, and then I've got a chloride ion, a chloride that has been produced, C minus. Now this charge is going to be balanced in that there's going to be resonance that we are going to be able to see. So we're going to have different structures that can be drawn for the same formula. That is basically resonance. So resonance is important because it stabilizes the compound. So what are we going to be able to see? This bond can move, and then it's going to form a double bond at this position. This carbon which is here add one bond, two bonds, three bonds. The fourth bond was the hydrogen. If this double bond moves out of here, it means that it is now going to only have three bonds. One bond here, two bonds, and then the third bond to the hydrogen on top. So because it has got fewer hydrogens, it's going to remain positively charged. So you can see the positive charge has moved. Another thing that we're able to do is that this bond is able to move up to there. So we're going to have here, here, and then a double bond there. This is the one which is going to be positive. Another thing is this bond is able to move here. So we're going to have a double bond here, and a double bond there. So this is the one which is going to remain positive. Now, these structures are going to be together in resonance, meaning that every time you have got a chloride being lost, these positive charges are going to be rotating on the carbon atoms like that to be balanced. And so, because they're always rotating like that, this compound is going to be stable like that because it is in resonance. And then the next thing that we're going to do is we're going to pick one of these structures which is in resonance. Let me pick the one which had formed at the beginning, which has got a positive charge here. Now we are going to attack it by the water here. So we're now going to have the water. The water is going to come and attach to this portion. And so what we are going to be able to see, we have got this point. So this is positive. We need the negative portion of water to attach to this positive. So, and that is the oxygen. Of course, we have got two hydrogens like that. Now, oxygen has got three bonds. It's going to be positively charged because it has got more than enough bonds for it. Again, the next thing that we're going to be able to see is that one water molecule again is going to come and grab one of these hydrogens, and then this bond is going to be broken, taking the electrons there. And so what we're going to be able now to see as a final product is going to be like that, the oxygen with only one hydrogen, and then we have also formed H3O plus. So this is the reaction mechanism, and then this is the benzyl alcohol. All right.